This first simulation shows the potential energy difference between the unbonded state, shown here, and the bonded state, which is a naturally occurring process here. This is the bonded state, low in potential energy. The unbonded state is high in potential energy. It requires energy to break a bond. The bonding process is natural. These will automatically come together. We can try to break the bond using energy. In this case, the bond breaker that falls from the sky has an energy of 400 kilojoules per mole, which you can see is not quite enough to break this bond, but is enough to stretch the bond out, and it will naturally then rebond in its low energy state. In order to break the bond, I'll need to increase the bond breaker energy. Here I've increased it to 500 kilojoules per mole. With this amount of energy, the atoms will be separated and the bond is broken. My second simulation shows a different bonding pair. This is a hydrogen and a fluorine atom, so we'll be making an HF bond. You should be able to see here that the initial state is very similar, but the bonded state drops down into a deeper well. It's very low in energy, and this makes a stronger bond. As we watch this simulation here, the bond breaker energy is 500 kilojoules per mole, which was plenty to break the previous bond, but is unable to break this stronger bond. We can say that this low energy state, this very low energy state, is stable. So this is a stable bond, it's a stable molecule. The bond breaker attempts to disrupt it, but is unsuccessful because of the strength of the bond. Although this is a strong bond, if I crank the bond breaker energy up to 700 kilojoules per mole, it will separate. Some students find it paradoxical that the lower the energy of the bond, the harder it is to break, the more energy it takes to break. But based on this model of a well, it should make sense to you that the lower the energy, the more energy it takes to break. This is simulation number 3. So here you can see we have unbonded atoms that have high potential energy. And then we have this interesting triangle here, which is labeled heat energy. The bonding event is actually going to create heat. This heat in reality does not exist until the bond is formed, and then out it comes. So here I'm covering up the heat energy. It doesn't exist yet. And then suddenly it's there. So this bonding event is how heat is produced in chemical reactions. The formation of chemical bonds makes heat. Although this may look like the creation of energy, it isn't creating any energy. It's simply transferring potential energy into heat. This is simulation number 4. Here I'm trying to demonstrate the concept that we are neither creating nor destroying energy. Energy can never be created or destroyed. And I'm using numbers to help prove this concept. Here you can see these atoms unbonded have high potential energy. When they bond, they will drop in potential energy. At the moment of bonding, heat is produced. the amount of heat, 600 kilojoules, is the difference between the initial and final potential energy. Essentially, we lose 600 kilojoules of potential energy traded in for 600 kilojoules of heat energy. No gain, no loss, simply a trade. Once again, this heat energy does not exist until the bond is created. This is the final simulation, simulation number 5. Similar in concept, but the numbers are different. The sound is lazier. This is not as energetic as the previous one. If you look at the numbers, potential energy starts high and ends lower, but the difference is only 400 kilojoules per mole. That's why this heat energy that's produced is only 400 kilojoules. And once again, it does not exist until the bond produces this heat as the potential energy of the atoms drops.